So, welcome to our 3.7 lecture. What I'm going to talk about today is something called an improper integral. And what an improper integral is it's an integral in which the bounds are not traditionally defined, right? Okay, either we have one of two problems. One of our bounds happens to be infinity or negative infinity, or two, we happen to have a discontinuity, normally an asymptote, at one of the values, either within the interval or at the ends of the interval. And so it turns out that being able to actually integrate these kind of functions is really important and really handy. For example, one of the ways that we might see this is inside of the normal distribution inside of statistics. So the normal distribution is what we might call something like it's called a PDF, or a probability distribution function. So we've got this function f of x, and we're not going to get into what exactly the function is. It's kind of long and involved, all right? But what it basically looks like is it looks like this. So here's our x-axis, okay? At the center, we'll have 0, okay, our y-axis, and I'm going to imagine, not imagine, but there's a bell curve, right? So that's exactly what this looks like. Now, as I get closer and closer and closer to, or as values get larger in the positive direction, we have an asymptote at y equals 0, and we'll have another horizontal asymptote as we go to negative infinity, also at y equals 0. Okay, and so what we often want to do is we're often going to want to figure out what the, say for example, the area is before a particular value on this interval. So like say for example, we got x equals 1 right here. Okay, we want to know what is the area. I want to know the area of f of x dx, okay, from the end of the interval all the way up to 1. Well, I got a problem, and the problem is this. I've got the end of the interval is actually at negative infinity because my curve actually never actually hits the x-axis. All right, it actually gets really close, but it never actually hits. So I'm going to go from negative infinity up to 1. Well, the problem is that if I'm looking for a definite integral, and that's what I'm looking for an actual value. I want to know, right, what this number is. Well, how is it that I'm going to be able to do that? Right? Okay. And that's basically the question that we're going to ask ourselves inside of this lecture today. So we're going to utilize this idea of an improper integral. So let's start out with, there's going to be a couple of different definitions that we'll utilize here. And each one has to do with like a different circumstance or a different occurrence. So we'll start out with the first one. And we first want to start out with that f is continuous over an interval of the form a to infinity, and that's positive infinity. Okay. Then what we're going to try and do, our attempt is going to be to take the integral from a to infinity of f of x dx. Okay. And if we can do that, what we're going to do is we're going to end up with, that's going to equal the limit as t goes to infinity of a to t of f of x dx. Now this t is going to be what we call a dummy variable. And what it means to be a dummy variable is it means that we're going to let it stand in for our value of x, okay, because we know what a is. We're going to figure out what a is, or the integral for a, and then we're going to substitute in t, and then we're going to take the limit as that value of t goes to infinity, okay? You might ask yourself, why not, just utilize x again? And it's because x actually happens to be the value for our function. And what we're looking for is we want to figure out what the value of the integral is, a definite integral. We want to know the value for the definite integral. So substituting in the t prevents a lot of confusion for us. Okay? All right, let's take a look at an example, and I think that'll help us out quite a lot. So let's take a look at this example. What we want to do now is we're going to want to find 1 to infinity, the integral of 1 to infinity for 1 over x dx, if it happens to exist. And so we might say, okay, well, okay, why does this matter? Here's why it matters. Let's we don't need to imagine what this looks like. We know what this looks like, okay? We'll draw this graph, and the graph is going to look kind of like that. We know 1 over x has an asymptote at y equals 0, okay? And so here we go, there's 1, and we want to know what is the area under this curve. And you might think to yourself, well, you know what? That this curve gets closer and closer and closer to 0 as our x's get bigger and bigger and bigger. So maybe I actually do have a value. Maybe it does exist. What we're going to do is we're going to test that out. We're going to see if that's actually true. So let's go in and let's utilize our definition for the improper integral. So I'm going to take my original integral. I've got 1 to positive infinity of 1 over x dx. And that's going to end up equaling, and I'm going to change this now to a limit. And I'm going to take the limit as t goes to infinity. So I'm going to make that dummy variable change. And I'm going to go from 1 to t. So the t gets substituted in for my infinity. Okay, so basically what it's going to do is we're going to get that value by taking the limit as t goes to infinity. We could get into it a little bit more. If such a value does exist, it should be that limit. Okay, that actually should be exactly what it should be. So we now have over 1 over x dx. Okay, now what I need to do is I'm going to integrate. So this is now going to continue to be the limit as t goes to infinity, and I want to remind you to continue to put that limit value, that limit as t goes to infinity. It's really important as you move through and progress through solving these things, because it communicates what it is exactly that you're doing. So now the integral of 1 over x is the natural log of x, and we're going to evaluate that from 1 to t. So this is now going to end up equaling the limit as t goes to infinity of the natural log of t minus the natural log of 1. Okay, well, the natural log of 1 is going to be 0, and so consequently we can it'll just go away. So we got the limit as t goes to infinity of the natural log of t. Well, this thing is actually going to end up equaling positive infinity because as t gets larger, the natural log gets larger as well. It gets larger slowly, but it still gets larger, and it never ends. Okay, it's going to just continue to get larger and larger and larger and larger without end. So consequently, this ends up being plus infinity. This means that the integral from 1 to positive infinity of 1 over x dx is divergent. What that means is that it doesn't exist because the value keeps going up to infinity. So we say that it diverges. It's a divergent limit. All right? So basically that's what we're going to do. We're going to see that a couple of other times. A couple of things to note. Make sure that you are writing in your limit notation. All right? And also, this is going to become really important, that the order of t is in the proper order. All right? Or else you're going to end up with the opposite of what you want. So let's take a look at a second case. And in the second case, we're going to allow f to be continuous over an interval of the form negative infinity to b. Then our integral from negative infinity to b of f of x dx will equal the limit as t goes to negative infinity of the integral from t to b of f of x dx, provided that that limit exists. So now what we're doing is we're going to be looking at the left-hand side of the function as it goes to negative infinity. And oftentimes this is going to be because we have an asymptote, again, just like we did in the first case. So let's take a look at an example of that. So let's find the integral from negative infinity to 0 of x e to the x dx if it happens to exist. All right, so what I want to do is I now want to imagine what this function looks like. Okay, it's an exponential function. And what we end up having is we've got this function that it kind of rockets up very high very quickly, right? It increases really quickly because it's an exponential times the value of x. And then what we're going to get is it's going to go negative, and it'll be on the negative side, okay, of the function, and we'll have this asymptote, this horizontal asymptote of the x-axis, okay? So what we want to know is what is the value for us? It's how big is that value right there? What is that value equal to? Okay. So what I'm going to do is I'm going to utilize my improper integral techniques in order to find what that integral is if it actually does exist. So I'm going to I've got the negative infinity to 0 of x e to the x dx, and this will equal the limit as t goes to infinity of the integral of t to 0, okay, x e to the x dx. Then what I'll do is I'm just going to I'll use the tabular method in order to go out and find this integral. I've got x and here e to the x. We'll use integration by parts. And this is 1, this is 0, here's e to the x, and this is e to the x. So this is going to end up equaling the limit as t goes to negative infinity. Okay, sure that that's clear there. Negative infinity of, and now this will end up being x e to the x minus e to the x evaluated from t to 0. Now we have to be really careful here. Make sure that our t's and our zeros are in the right places, right? Because otherwise we're going to end up having a switch sign. So we have the limit as t approaches infinity. I'm going to evaluate, or t approaches negative infinity, excuse me, of, and this will be 0 e to the 0 minus e to the 0 minus, and this will then be t e to the t minus e to the t. Now the e to the 0 e to the 0 minus e to the 0 is just going to be negative 1, and it's not going to be dependent upon t, right? So that's important because that means we can take it out of the limit. So now we get negative 1 minus, and this will be the limit as t goes to negative infinity of t e to the t minus e to the t. Okay, and so now our chief concern here is just to find this limit. What is the value for that limit? So we're going to set the negative 1 aside. We'll even set the negative aside for just a moment. And we're just going to concentrate on finding the limit as t approaches negative infinity for t e to the t minus e to the t. Well, the first thing I want to notice here is that I can actually factor out an e to the t. So this will be the limit as t approaches negative infinity of e to the t times t minus 1. If I evaluate that, what I'm going to end up with is I'm going to end up with e to the negative infinity, which is 0, times a negative infinity, because negative infinity minus 1 is still just negative infinity. So that's a problem, right? What I have here is I have, an undefined limit, all right? Or, yeah, I have an undefined limit. What I want to do is I'm going to utilize L'Hopital's in order to actually go out and solve this limit, okay? So I'm going to take the limit as t goes to negative infinity, and I'm going to make t minus 1 be my top and e to the negative t be my bottom. Okay, so if you've forgotten how to find some of these limits, especially using L'Hopital's or or some of those algebraic techniques, what I would recommend is that you make sure that you go back and watch some of those videos. They're inside of the course, okay, or on my YouTube channel inside of the Calculus 1 videos. Okay. But this is, pretty standard technique. Now what we're going to do is use L'Hopital, so I'll take the derivative, and that means that I'm going to get the limit as t approaches negative infinity of 1 over negative e to the negative t. Okay? Well, now what this is going to be is this is going to be 1 over, and this down here, well, that negative negative t is going to make it a positive infinity. Okay, so it's going to end up being e to the infinity, so it's going to end up being like negative infinity. All right, so it's going to get really big, and so consequently it's going to end up equaling 0. All right, and that's the value for our limit. Careful though, because that actually is not the value of the integral. Remember, the value of the integral has negative 1 and that minus value. So we've got now my value of my integral from negative infinity up to 0 of x e to the x dx is going to equal this negative 1 minus 0, or just negative 1. All right? So what we had to do here is, in addition to actually solving for, or finding our integral, okay, we actually also had to utilize our limit techniques in order to actually go find the limit. All right? And you may have to do that quite a lot throughout this section. So now we have a third case, and in this third case, what we're going to do is we're going to actually look at, well, what if I have an integral that I'm trying to find from negative infinity to infinity, right? Now I don't have that value that I can kind of bump up against, right, my a or my b. What then? Well, in this case, not so bad. What we're going to do is we're going to use the fact that we can actually go out and separate out integrals, right, and use addition in order to do that separation. So the integral from negative infinity to infinity of f of x dx is going to equal negative infinity to 0 of f of x dx plus 0 to infinity of f of x dx. And the truth is you don't actually have to use 0. You could use a or b or 1, negative 1, 12, 14, whatever value you want, because just so long as we are continuous on all of negative infinity to infinity, you're going to end up with the same value anyways. It's just you're going to have different values for each individual integral. Now, in addition to that, we have to make sure that both of these integrals, negative infinity to 0 and 0 to infinity of f of x dx, both exist. And otherwise, we are going to have divergence and the integral is not going to be defined. So let's solve this. Let's say we want to find the integral from negative infinity to infinity of x over x squared plus 1 dx if it exists. So when I look at the integral, here's what I'm going to see. Okay, if I want, I can go in and utilize algebraic techniques to show that I in fact do have an asymptote at y equals 0 as we go to negative infinity and positive infinity. Okay. And so consequently, it looks like that this might not necessarily, but it might actually exist. So what we're going to do is we're going to use the techniques that we talked about just a moment ago. So we're going to have the integral from negative infinity to infinity of x over x squared plus 1 dx is going to end up equaling, and this will be the limit as t goes to negative infinity of negative infinity to 0. X over, excuse me, not negative infinity, but the limit, yes, probably not yet, we'll get there, is going to be the integral from negative infinity to 0 of x over x squared plus 1 dx plus the integral from 0 to infinity of x over x squared plus 1 dx. Okay, now I'm going to do each one of these individually one at a time. Right, I got a little ahead of myself just a moment ago. So this first one here is going to be the limit as t goes to infinity, or t goes to negative infinity, excuse me, of the integral of t to 0 of x over x squared plus 1 dx. Now what I notice here is I've got a u substitution, so I'm going to let u equal x squared plus 1, and du is then going to equal 2x dx. That means that 1/2 du is going to equal x dx. So now what I have here is I have the limit as t goes to negative infinity, okay, of the integral from t to 0 of 1/2 1 over u du, okay? And so that ends up equaling the limit as t goes to negative infinity, okay, of 1/2 natural log of x squared plus 1 evaluated from t to 0. Okay. Now, so we have the limit as t goes to negative infinity. So now I'm going to plug in my values. I got the limit as t goes to negative infinity. Okay. And I'll pull out my 1/2. So I'm going to pull out my 1/2, and this is now going to be the natural log of, and this will be 0 plus 1 minus the natural log of t squared plus 1. And this is going to end up equaling then 1/2. This is 0 because the natural log of 1 is 0. So we end up with the limit, or 1/2 times 0 minus the limit as t goes to negative infinity of the natural log of t squared plus 1. Now, the limit, the natural log of t squared plus 1, the limit as t goes to negative infinity of the natural log of t squared plus 1, okay, because we're in absolute value, this is going to end up going up to positive infinity. Okay, that ends up going up to positive infinity for t. And so consequently, what that's going to end up equaling is that this is going to end up being 1/2, and this will be 0, right, minus, and this will be infinity, right, which is equal to negative infinity. So the limit diverges, and the integral does not exist. So consequently, we can stop right there, all right? Since this half of the integral doesn't exist, right, the one where the limit goes to the limit as t goes to negative infinity, that actually means so the entirety of the limit will not exist. You can't have 1/2 of the limit not existing, okay, and have the other one exist, and have the whole thing exist. It doesn't work. Let me restate that just so that it's clear. What happened here is that we had half of our limit, okay, or excuse me, half of our integral. The half that goes from negative infinity to 0 ended up being divergent. And since it was divergent, what we ended up getting was the entirety of our integral is divergent, All right, so it does not exist. All right, you have to have both sides exist. Okay, so this technique that we're looking at here can actually also be utilized when we're integrating on discontinuous intervals. So meaning like what happens if we actually have a discontinuous function that we are looking to integrate along, okay? Maybe for example that we have like a vertical asymptote, and that's probably the most common occurrence here for this particular kind of integral. So what we're going to have is we've got these three basic theorems. You may have to pause the video in order to, kind of take a look at them and write them down if you are taking notes. But number one, let f of x be continuous over the closed interval or the half open interval a to b. So that is that it's only closed on a and then it's open on b. B is going to be the place where we have a discontinuity. Then we'll have the integral from a to b of f of x dx is going to equal the left-hand limit, right, of a to t of f of x dx. So basically what we're going to do is we're going to take the limit as t approaches b from the left-hand side and see if we get a value for that if that limit does exist. If not, it's going to diverge. Then we let, number two is we'll let f of x be continuous on the half open interval a to b. And in this case, the closed part is on b, so what we have is we have the discontinuity at a. Then the integral from a to b of f of x dx is going to equal the limit as t approaches a from the positive side, okay, of t to b of f of x dx if that limit exists. And if it doesn't, then we have a divergent integral. 3. Then let f of x be continuous over a to b, and we have closed intervals for both a and b, except a point c in the open interval a to b. So this is some point c, not a, not b, okay, but just somewhere in the middle, probably, again, a place where we have a vertical asymptote. Then the integral from a to b of f of x dx, we're going to separate it out. We're going to have one integral go from a to c f of x dx, plus the second one, c to b of f of x dx, provided that both our integrals, a to c of f of x dx and the integral c to b of f of x dx both exist. All right, so if that's the case, then we actually do have a value for this integral. We'll just have to separate it out and utilize our limit properties in order to go out and solve for that particular limit. So let's take a look at this particular problem. Let's say we want to find the integral from 2 to 5 of 1 over the square root of x minus 2 dx if it exists. Now, we know that x cannot equal 2 for f of x, and so we have a discontinuity there. All right, and if you look at it, that discontinuity is going to end up being a vertical asymptote. All right, we essentially have something that kind of looks like this. Okay, here's 2, here's 5. Okay, and our integral is doing one of those things like there. Okay, except for our asymptote is actually at 2. So here's our asymptote, and we want to know how big is this area underneath that curve. Okay. So that's the problem that we're interacting with, or that we're dealing with. So one, we've got to get that whatever limit I'm going to get is going to end up being the limit as we get 2 from the positive side. Okay, it's really important that we get that, because from the negative side we go up to infinity, but like you could end up with a different infinity. There's all sorts of issues. You just got to recognize that we're going to be coming from the positive side here. Okay, so our integral, the integral from 2 to 5 of 1 over the square root of x minus 2 dx is going to equal, it'll be the limit as t approaches 2 from the positive side, okay, because we're looking at like the lower end of our interval, of t to 5, 1 over the square root of x minus 2 dx. Now we'll use a u substitution in order to find this integral. So u is going to equal x minus 2, du will then equal dx. And so what we get here is this is going to equal the limit as t approaches 2 from the positive side of the integral of t to 5 of 1 over the square root of u du. Okay? Now, we're going to integrate that, so we're going to get the limit as t approaches 2 from the positive side, and this is going to end up being u is going to end up being 2u to the 1/2, right, from t to 5. And when we substitute, this will be the limit as t goes to 2 from the positive side of 2 times the square root of t minus 2 evaluated from t to 5. Okay? Now, this is actually, it's kind of great. What we're going to get is first we're going to substitute in just 5 straight up. So I'm going to get 2 times the square root of 5 minus 2, and I can take that out of the limit because it's just a value. It's not dependent on t, right? Minus the limit as t goes to 2 from the positive of 2 times the square root of t minus 2. Okay? And so this ends up just equaling 2 times the square root of 3, right? Minus, and then we could just substitute in directly. We can do direct substitution here because there's no problems anymore. So this ends up being minus 0, right? Substitute in the 2, you get 0. So we get 2 root 3. And that is the value for our integral. So notice that all we needed to do was we needed to notice where the discontinuity was. Since it was on the bottom end of the integral, we utilized that limit as t approaches, in this case, 2 from the positive side, right? Because we wanted to see, we were going to want to go from the positive side. And then we basically solved it like we would with the ones with regard to infinity. All right? And so this ends up giving us the value for our integral. So let's take a look at this integral. We want to find the integral from 0 to 3 of 1 over x minus 1 dx if it exists. So what we know is that we have a discontinuity at x equals 1. X equals 1 is a problem. All right? X equals 1 is in the middle of this interval. So consequently, what I'm going to do is I'm going to split up my integral. I'm going to make it 0 to 1 of 1 over x minus 1 dx plus 1 to 3 of 1 over x minus 1 dx. And that will then allow me to evaluate both my integrals individually. So we'll take the first one. Let's see if this one exists. And if it does, what is its value? So the limit as t approaches 1, this time it's going to be from the negative side because 1 is on the top end of my interval. 1 over x minus 1, or the integral of 1 over x minus 1, evaluated from 0 to t dx. This is going to end up equaling the limit as t approaches 1 from the negative side of the natural log of x minus 1. You can find that using a u substitution if you're inclined. Evaluated from 0 to t. Okay? Now this is then going to equal, all right, the natural log of 0 minus 1 minus the limit, or excuse me, pardon me, it's actually going to be the limit as t approaches 1 from the negative side of the natural log of x minus 1, natural log of, t minus 1, minus the natural log of 0 minus 1. And remember, that's one of those things, I just got to demonstrate a little bit of an error for you, where we flipped the direction, right? You don't want to do that. It's going to flip your signs. That causes all sorts of problems. Okay, so this is going to then end up equaling, okay, this will end up equaling the natural log, and this value is going to approach 0. Okay, so this one's going to approach 0, and so what happens as natural log approaches 0? Well, then the value of the natural log goes down to negative infinity. That's a problem, right? This is going to end up being negative infinity minus, and this is 1. That's great, but yeah, negative infinity minus 1 is still just negative infinity. So the integral diverges. And just like in our last occurrence, okay, if one of those two integrals diverges, then the whole thing is going to diverge, right? You can't have just one value. So consequently, this integral, we don't have a value for it. Yeah. So this finishes up the lecture. What we discussed here was basically how do we find integrals when we have discontinuities or when we have something that's not as clearly defined as is just having a particular value, right, in terms of the definite integral. So like what happens if we have an integral that goes from negative infinity to infinity, or if we have one where we have a discontinuity in the middle of the integral, what do we do then? Okay, so all of these practices that we've been talking about are all to deal with those particular problems or issues. Okay, so this completes the lecture.